चलिए ठीक है ओके सर
Good afternoon, ma'am.
Yeah, good afternoon. Are the students there?
Ma'am, I have shared the link. They'll join within 2 minutes.
Okay. I just want to finish uh, this lecture. I don't think it'll take much
Yes,
time
ma'am.
so that we can start.
Okay, ma'am, no
I'll
problem.
go because as a meetings, sometimes you have to go to the department, so it becomes difficult to take class.
Yes, ma'am.
कल भी busy है सुबह. I just finished the meeting, so I thought अभी time है, we can take one at least 45 minutes class. Just a second. Did you have any class this morning?
Yes, ma'am. Morning में नहीं हुई है. अभी afternoon में हुई है हमारी बस एक operating system.
Taking operating system or with ma'am? तहूर मैम ले रही है?
Yes, ma'am. ताहूर मैम ले रहे हैं.
Okay. Around 40 people have come. Just scan the list from time to time. If you find somebody who is not from the class, just let me. You can just message me.
Yes, ma'am. Yes.
Okay. Okay, so let's start the class. What we were doing in the last class was how to solve recurrence relations. So we did substitution and iteration method. There are two more we have to do. Changing of variables is also considered like a separate method, but you just change the variable and then you solve it by any known method to you. For example, substitution, iteration, or even recurrence, this recursion tree. Okay, so the two more ways we have to do is recursion tree method and master's theorem. Okay, so what is the recursion tree method? If you remember, I think I did draw a tree in one of the lectures on merge sort or quick sort, that the number n, if you have to sort n elements, the problem gets divided into n by 2. So you create like a binary tree for that, you see in a while. And then we see how many leaf nodes are there, how long does it take to solve one leaf node entry, and then if there are n leaf nodes, so that will be the total time, and what is the cost at each level. So you'll get to know what we mean by that. So if you see this problem, this is again the same recurrence relation for merge sort or quick sort, for ideal case of quick sort when you have equal partition of the array into two parts. So in merge, we spend extra time in merging merging the two sub arrays so that the resulting array is sorted. So that we discussed in that class only, that the time it takes is at least n comparison, at least at the most n comparison. So, and also in quick sort, when you divide the array into two parts, you compare the elements. So at the most, you will make n comparisons. And that is the Cn part of this equation. Tn is to Cn by 2. Just a second. Okay, so Tn is your initial equation. So Tn is equal to twice Tn by 2 plus Cn. So when I go to the next stage, the Tn part is divided into Tn by 2 and Tn by 2, and you are left with Cn. Cn is some extra work that you do. So this work in case of merge sort comes into picture when you are merging this Tn by 2 and Tn by 2. In case of quick sort, it comes into picture when you are dividing using the pivot element. So this Tn by 2 will again be equal to twice Tn by 4 plus Cn by 2. So how you do that? You just replace in the original equation here. You replace Tn by n by 2. So you'll get twice Tn by 4 plus Cn by 2. So this is what you get. Okay. Another level, when Tn by 4 gets divided into Tn by 8, you will have uh, 8 children in the next level. Okay, so keep on doing it. If you see your iteration method, what do we do there? We replace Tn by Tn by 2, then n by 4, then n by 8, and then we say the pattern is it's n by 2 to the power k. So ultimately n is equal to 2k, and you want to get actually to t1. So this tree will continue, and this will go all the way down to the leaf node where n is equal to 1. So your Cn will be just C. Okay. This is a binary tree. We know if there are n nodes in a tree, the height of the binary tree is log n. Okay. If you remember, we did the summation. We'll just come to that in a while. So at level, the root level, you do Cn work to split it. In the next one, you do Cn by 2 work and Cn by 2 work in the left side and the right side. So there are two jobs of dividing. So you're dividing n by 2 further into n by 4, and you're doing it twice. So the total cost is 2 into Cn by 2, which is again equal to Cn. So 4 times Cn by 4 in this level, if you go horizontally, there are 4, you see 4 Cn by 4, which is equal to Cn. And how many leaf nodes will you have? If you have 10 elements in merge sort, when you get down to the leaf level, you will have 10, obviously 10 leaf nodes. So there are n leaf nodes, and the work that you do, if each level, each leaf node is 1, there are n leaf nodes. Okay. So what is they've written theta n, it is again n. So the height of the tree is log n at every level. Height is number of steps it takes from root to the leaf node. So if it is 3, so height is 3 into 3 times Cn will be your answer. In this case, height is log n. So Cn into log n, which is n log n, which we know is true for this. Okay. Okay. Let's get it. Another example. It's the same problem. Wn is equal to twice Wn by 2, but the additional cost in this case is n square and not n. Okay, so if you see the tree here, so this tree n square gets divided into n by 2 square, which is n square by 4. So when you add n square by 4 and n square by 4, that is twice n square by 4, which is n square by 2. Similarly, when you do 4 times n by 4 whole square, it is 1 by 4 n square. Okay. So again, when will you get to this W1? When you arrive at the leaf nodes, you will get down to Wn, and how many of those will you have? So if you look at the left hand side here, you have Wn by 2 is twice Wn by 4 plus n by 2 whole square, and Wn by 4 is n by 2. Just let me see, we'll do it. Okay, it's here. So you get down to W1 when this here n by 8, this n by 8 here should get down to n by 1. Sorry, it should get down to 1. Let me do it. I'll show it to you here. So if you generalize this equation, and let me use the whiteboard, W twice Wn by 2 plus n square. So Wn is Wn is equal to twice this is substituting n by 2 with n by 4. So plus n square, right? So this is equal to, so it's 2 cube W n by 2 cube plus n by 4 whole square gets multiplied by 4, so it is 4 into, let me just write it down. This is outside, this gets multiplied with, okay. So if we are solving this problem using iteration, we will say that we will put n is equal, first we'll write the generalized equation, which will be 2k W n by 2k. 3 is your k now. So this is 1 by 2 k minus 1 n square by 4. So I'm cancelling out 1 4. So I get n square by 4. Okay, sorry, 4 has to go. Okay, so this 1 4 gets cancelled, so you have n square by 4. 4 is 2 to the power 3 minus 1, so 2 to the power k minus 1. Similarly, you get n square by, this will be so on, and you'll have n square by 2 plus n square. Okay, so this is my generalized equation. So if you see this term here, when n is equal to 2k, I will get W of 1, right? So what will this whole thing become? This whole thing becomes n into W of 1. W of 1. And then I have this series which I have to take care. Okay. So if you see here in the slide, so how many W1s we got? We got n W1s, right? That is here. If you see, you have the sum of the series n square by 2i. I goes from 0 to log n minus 1. So plus this n times w1, that n is here. Change its color. Okay. So n, you take n square outside and you have sum of the series 1 by 2 I, which is roughly, they're taking the infinite series 1 by 1 minus 1 by 2, which is 2n square plus on. So when you get a n square and you get on, you take the higher of the two, it is 2n square. Okay, so wn is on square. So again, similarly, this problem, here you have 3 subproblems, so it's not a binary tree now. It is a, it's a tertiary. There are 3 children of the tree. So your cn square gets, if, how do you get to the next level? How do you get these values at the next level? You replace n with n by 4, so you will get 3 times n by 16 plus cn by 4 whole square. Okay, so you get 3 of those and you get these subtrees. Okay, now how do we get the height of a binary tree? If you remember, we calculate the sum of all the nodes at every level, and then that is equal to n, and then we calculate. If you go back to how we calculated the formula here. Okay, let me, tn is 3, tn by 4 plus cn square. Let me, so tn is 3t n by 4 plus, I'll just write n square, just forget this thing. This is 3 n by 16 n by 4 plus n square. Again, just write 3 square and then tn by 64 plus n by 16. Okay, tn by 16 is square so you get 3 square, no sorry, this is 3 here, get 3 cube tn by 4 cube plus 3 square into n by n square by 4 square plus 3 into n square by 4 plus n square. So this, if you generalize, you get 3k tn by 4k plus, now you have 3 square here, so 3k minus 1 n square by 4 square, this is also 4 square, plus 3, this will be k minus 2, and so on, this will go up to n square. Okay, so now if you look at this part, to get t1 we need n to be equal to 4 power k, which means log, just apply log on both sides, k log 4, get k to the left sides, you have log n by log 4, so this will be k, when they're of the same base, it is log n to the base 4. So your k is log n to the base 4. And what will be 3 to the power k? It will be 3 to the power log n to the base 4. So then there will be this summation. So if you go back to the slide, so I or rk is log n to the base 4. What is the cost at each level? It is n by 4 to the power I, whatever level you are, whole square. And the last, how many nodes does the last level have? So if you go back here, let me see on the whiteboard, how many nodes, how many T1s do we have? How many T1s? We have 3 to the power k T1. So how many nodes at the leaf level? So normally in a binary tree, when we keep on dividing equally, you get, so how many T1s? Because now you are dividing by 4. You have 3 to the power k T1s, which is k is log into the base 4. So this is the number of nodes at the last level. So when you have 3 to the power log n to the base 4, you can replace. If you get n down, you can take 3 up. So n to the power log 3 to the base 4. Okay, this is a formula. You can just revise those. So because we want in powers of n, we don't want n in the power or in the, so that won't help us actually be able to tell definitely what the total runtime is. So if you see here, this is what we got at the, there are so many T1s. So whatever, if, let's say the cost of one, the problem with one n equal to 1 is 1, then you have n to the power log 3 to the base 4. Okay, and then you have the sum of the series. This is the from 0 to k minus 1. Your k is log n to the base 4 minus 1. And they, it is obviously less than the sum of the series up to infinity. So they again apply the same geometric progression for infinite series and they get n square. N square is obviously there. They get 1 by 1 minus 3 by 16, which is a constant. So constant into n square is considered to be n square. And n square is greater than n to the power log 3 to the base 4. Okay. This, obviously you won't just see and follow it. If you don't, if you cannot figure out whether n square is greater or log 3 to the base 4 is greater, just put in some values and find it for yourself. Then if you see a pattern, growing pattern, n square is greater than n to the power log 3 to the base 4, then you can safely say it is O of n square. Okay. Now sometimes, this is again a simple example where all your leaf nodes, they terminate at the same level. What I mean by the same level, if you look at this kind of a recurrence relation, you have one partition where Tn is divided into Tn by 3. And there's another partition where Tn is equal to Tn by 3 plus T twice n by 3. So if you put some value, let's say n is equal to 3, you will get T3 is equal to T1 plus T2, right? So T2 you have to go down to, again, basically what I'm trying to say is when you have unequal partitions of the subproblem, one partition might reach T1 faster than the other partition. That means the, if you count the height from the root node to that T1, that will be lesser than the height for the another branch. So if you see here, okay, let me write it down. Tn by 3 plus twice T2n by 3 plus n. So if we have this Tn by 3 plus twice T, sorry, not twice, T2n by 3 plus n. So Tn, let's say what is Tn by 3? Tn by 3 is Tn by 9 plus T2n by 9 plus n by 3. And what is T2n by 3? That is T2n by 9 plus T4n by 9 plus 2n by 3. So your Tn, the board is too small for this, is equal to, I'll add these two, Tn by 9 plus twice T2n by 9. I have these common terms plus T4n by 9 plus n. If I take n by 3 common, I get 1 plus 2. Okay, so this is just the first step. Let's say I just put this first step in terms of powers of 3, just to give you an idea. I don't have space to expand it any further. 2 into n by 3 square plus if you have to generalize this equation, so I can write something like this. If 2 is k, two by 3 k into n plus n by it has to be expanded once more to see the pattern, but what I want to tell you is this n by 3k and 2n by 3k, if I put n is equal to 3k, so k is log n to the base 3. Okay, and if I put 2n is equal to 3k, so that I can get t1 in this case, so I write it here. You get 2 log n is equal to k log 3. Sorry, no. Again, my battery is low. Okay. So basically what, if n is equal to 3k, you will get t1 here. And if n is equal to 3 to the power k, you get t2 here. Okay, so t2 means t2 is not the leaf node. T2 can be divided further. Obviously 2 is not divisible by 3, but when we talk of in terms of powers of 3, so T2 branch will be longer. So if you look here, I'll just rub this and then I'll show you how. If you look here, the branch where you have n by 3, n by 9, n by 27, that branch will have a height of log n to the base 3. And the branch where you have 2n by 3, 2n by 9, 4n by 9, you will have log 3, to the base 3 by 2. So yeah, I have put it here. So, and in case for let me go back to this whiteboard. So let me erase a little part here so that I can write. So the longest branch will be this one. So if I write it down as n divided by 3 by 2 whole square. So when, or 3 by 2 whole square, or 3 by 2 to the power k. So if n is equal to 3 by 2, this is the longest branch, then you have log n to the base 3 by 2 equal to k. Okay, then this will be the longest branch, and the height or the number of steps from root to the leaf node will be these many. So if you see here, you get different. For one branch, you have to arrive at T1 when n is equal to 3 to the power k, and another branch you will arrive at T1 when n is to the power 3 by 2k. So accordingly, you will calculate. So overall, what is the height of the tree? It can be one branch can end at log n to the base 3, another branch can end at log n to the base 3 by 2. So the height is of the order of log n. Forget about the base, it doesn't matter, just for our calculation. So what is the work that is done at each level? At each level, you divide n into n by 3 and 2n by 3. And if you add the work, this is the work that you're doing, additional work, other than splitting the problem into two parts, whether equal or unequal in any way. This n by 3 and 2n by 3 is the extra work you're doing. Add the two, because that's the work done at level 1. So at level 1, the total work is n. Obviously, the level 0, total work is n. If you see in the next level, if you add all of these from left to right, then it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9n by 9, which is again n. So it is n into, what is the longest chain? Log n to the base 3 by 2. So you can keep it, but when we write the timing, we don't write to the base because it doesn't matter overall. It follows a logarithmic order. It's a logarithmic function. Whatever base it is, it will not affect that much. Okay, so we take the longest branch and we multiply that. Overall, the height is of the order of log n to some base. Okay, and every level you do n work, there are log n levels, so it's n log n. Okay, so this was how you do in recursion tree. What you have to do is you draw a tree like this. You can have a separate tree which says T1, sorry, Tn is Tn by 2, Tn by 2. And you draw a separate tree for whatever additional factor is there, plus n or plus n square, and see how it goes. Then you do the addition of that n across the level at each level, and you'll see a pattern. Either you'll see n, or you'll see, let's say, some kind of a arithmetic or a geometric progression. You basically have to add this n at all levels. So if you know how many levels are there, you just do n into number of levels. If it's not as simple as having n at every level, if it's like, let's say, 1, 2, 3, 4, 5, so on up to the last level where it becomes n, then you know it's sum of a simple arithmetic progression, n by 2 into 1 plus n. Okay, so that then you'll do it that way. Now the next way of solving is the most easiest. You just have to remember this theorem. You don't have to prove it, not at this level. You remember this theorem and you apply this theorem. Okay, so what does this theorem say? Normally you'll see a recurrence relation where you have Tn on the left hand side, and you'll have uh, very rarely you'll see Tn minus 1, n minus 2. It's always Tn divided by something, and that means you're dividing the subproblem, and how many subproblems are there, that is A. So you have, if you see on the right hand side here, you have A subproblems, and the size of every subproblem is n by B. Plus you have some function, which is this is the additional work I was talking about. So at every level, or for every n, you have to put some additional work Fn to do your job. Okay. So this n by b, you can take either the floor or the ceiling, that will not matter. So a and b are constants. A is greater than or equal to 1, and b is definitely greater than 1 because you don't want to divide by 0. They are constants. F and b are function. Now you have an idea how functions grow, right? N square, log n, you can have anything on the this after this plus, and then you'll know how many subproblems are there. So you know how much work is done at every step. As you divide the problem into subproblems, plus you have to do this Fn work. Okay. So the master's theorem says that these are the three cases. Normally, in some places, you'll see a fourth case as well. But let's first go about these main three cases. So you have case 1, case 2, case 3. What they do is they examine the function Fn. So if you go back and see what affects the final runtime, it's usually the sum of the series. Like I said here, you have the cost at every level is Cn, and you're doing Cn into log n, that's the height. Okay, what was this Cn? This was this function Fn in this case. Okay, if you see in this case, your this function n square here, this is what is become n square, 1/2 of n squared. Like I said, in this case, you have to do sum of this series. Okay, and this is the sum of the series. Sorry, here, not able to write. Okay, this n squared 1 by 1 minus 1 by 2. So again here, the sum of the series is what is affecting your main runtime, because that theta O log 3 to the base 4 is less than. You obviously have to check which one of the two is greater, but mostly this function will determine how your runtime is going to be. So again here, the work done at every level was n, so n into log n. So now in Master's theorem, this Fn is what we uh, basically focus on, and then we compare it with, we are see what we are comparing it with. So if you remember, to find T1, what do? We first generalize the equation. We get Tn by 2 to the power or 3 to the power something, and then we say we put n is equal to 3k and k is log n, or n is 3 to the power k. So basically, it uses that factor. So when you have to apply Master's theorem, first you have a look at the function fn, whatever it is. Okay, then you calculate this highlighted thing here, n to the power log a to the base b. Okay, forget about this minus this epsilon for now. Calculate that. Okay, then look at your fn and look at this value, n to the power whatever comes, and then try see the relation. Okay, for some so epsilon is a constant greater than 0. So to get a kind of relationship between fn and this term within the brackets here that I have highlighted, you can use an epsilon which is greater than 0. So you can subtract something so that you can derive some kind of a relationship between the two. So Tn is if fn is O of this value that you are getting, the highlighted value, that means if fn grows at a slower rate, that means if fn is less than or equal to O of this, for some constant epsilon e, or you can say just e greater than 0, then your Tn will also be O of this. Okay, and if it's not O, if Fn is theta of n log a to the base b, then Tn is will be equal to this. Okay, this is just a simple thing, simply put, and you have to apply this. We'll do some examples so you'll find out. And third case is if Fn is omega. So in this case, the difference is you do a plus epsilon. If Fn is omega of n, first of all, you find log a to the base b, then raise n to the power this, and then you decide for some epsilon value greater than 0. Now there is an additional condition in case of the third case here. It's not working. So other than checking this part here, you also have to check if this condition is true. A f n by b is less than or equal to some constant c into fn, and this constant has to be less than 1, and all sufficiently large n, then Tn will be theta of Fn. Okay, so you have to remember this to apply it. So what does this case is basically tell you? Like I said, you compare Fn with n log a to the base b. And if log a to the base b is greater than Fn, which is your case 1, because Fn is O means Fn is less than, then Tn is also O of this. You can say O or theta, that doesn't matter. Second case is if Fn is equal to this, then Tn is equal to n log a to the base b into log n. And third one is Fn is greater, then Tn is theta of F. So if Fn is greater than what you're getting from the leaf nodes, for example, then you just straight away put Fn as the final answer. So let's see one example. So first of all, whenever you have Master's theorem, forget about this highlighted part, just calculate n log a to the base b. So your a is 4 and b is 2, so you're calculating log 4 to the base 2. So what is 4? 4 is 2 square. Log 2, 2 square is 2 log 2 to the base 2, which is n square. Okay. Now, according to the formula, we have to subtract some epsilon value minus e. And then we have to compare it with your Fn. What is your Fn? Fn is n. Is n O of n square? Yes, it is. Now, but we have to see n square minus epsilon. And epsilon is less than 1. So let's say I put 0.9. Even then, I get n to the power 1.1. So n is less than n square. So case 1 applies. Now look at the second example. Again, n log a to the base b is n square. Your Fn is also n square. Okay. So if you try to apply first case, you have to subtract some epsilon from n square on the right hand side. If you subtract something, your case 1 will not be true. So basically n square and n square are equal. If you look at case 2, if your Fn is theta of n log a to the base b. So Fn is also n square and this value you get is also n square. So case 2 applies. So what is the answer in case of case 2? Then Tn is n square log n. Okay. Similarly, this is the example of case number 3. You have to figure out which case it belongs. So your Fn is n cubed, and again you are getting n square when you do n to the power log a to the base 2. So n square, n cube is obviously greater than n square. So n square plus some epsilon value, which can be, let's say, 0.1. So epsilon is greater than 0. So yes, so it will be 0.1, for example. So your so case 3 needs another equation to check, which is a a into f of n by b, which they're doing here. A is 4, n by b is 2 cube. Is it less than or equal to c into n cube for some c greater than 1? So you get 1 by 2 on the left hand side. So you choose a constant c which is less than 1, which makes this equation true, and you'll get the Tn is equal to theta n cube. So again, more examples. So you, let me see how many I've put. Tn is let me plus n log n. Are you able to see the PDF, the presentation, or just the whiteboard?
Whiteboard.
Okay. So first step, a is 2, b is 2, n log 2 to the base 2 is. So now I have n log n, which is my function. I have to compare it with n to the power 1. Okay, this comparison is what will tell me whether I am in case 1, 2, or 3. So what is your fn? Fn is n log n. Okay, and is n log n, is it O of n? Is n log n theta of n, or is n log n, in this case it is, actually it is 1 minus epsilon. This is 1 plus epsilon, which is greater than 0. And so which one is true out of the 3? If you remember, in the last class I showed you that graph. So where did n log n lie? Does it lie above or below?
Above, ma'am.
It is above, right? So that means it is greater than n to the power, let's say I put epsilon as 0.1. But then I am falling into case 3. And in case 3, I also have to check. So what is your A is 2? Sorry, let me just rub it a bit. I need some space. Okay, 2 f of, let me not write f. It's difficult to write on this. So 2 f of n by 2 is n by 2 log n by 2. Right? I'm just substituting. f of n by 2 in n log n. This should be less than or equal to some constant into n log n. So 2 and 2 cancel. So I get n log n minus n log 2 less than or equal to c into n log n. So even if the c value should be less than 1. Okay, so n log n minus something looks like it is less than c into n log n, and c is less than 1, so you can, for sufficiently large n. So let's say if c is 0.9, for example, scrap it off. If c is 0.9, that's the highest, for example, you can take, and n I'll put sufficiently large, let's say I put 2 to the power 10. I'll just substitute the values. 2 to the power 10 log 2 to the power 10 is into 10 minus 2 to the power 10 log 2 to the base 2 is just like that, 0.9 into 2 to the power 10 into log into 10. Okay, so this is so this is, I think, I hope I'm doing it right. Okay, so for this value we get it equal. So if this is 2 to the power 20, then definitely this side will be greater because you'll get, so this is true for c equal to 0.9. You can try it for some higher values and see what you get. Should be true further on from this as well. Okay, so if you are in the third case, you have to prove this for sufficiently large n, and for this c is less than 1. So you have more examples in the slides which I'll post later on. You can just, I'll send you more examples to do with answers so that you can do it and then check. I'll send you a PDF as well. There are online some notes. I think I'll post them. I think I'll post them on the class. I'm in the classroom only. There are some notes. You don't have to, they might have some additional information which you do not need to study. You can just study those parts that are relevant or similar to the class lecture notes, because these I make from random notes and I put them together. So these are the things you need to know. There might be details of proofs and other things for theorems. You don't have to do that. What you have to do is learn what the Master's theorem is and be able to solve problems like this. So for example, you have here, in this case, log a to the base b is log 1 to the base 5. Okay, log 10 is 1 and log 1 is 0. So n to the power 0 is 1. So your fn is also 1 and your this value is also 1. So it is theta of n to the power log a to the base b. Okay. So similarly, second one you see, fn is n and log, this is again theta, n into log n. This is case 2 when it is equal. So this is case 3 where you have to look for some c value. Fn is n square and that is n. So Fn is greater than your value of n to the power log a to the base b. So you have to verify this condition again. And if you see, this condition is true when c is greater than or equal to 3 by 16. So it is n square. So similarly, This is case one, and you just go through them. I'll send you more examples. So better do it on paper. Take the problem, do it on paper, and then check with the answer in this slide. Okay, so this covers your basic mathematics that you will require. So one you need to know how to evaluate a program by just looking at it. You don't have to be very specific following each statement. Just know the rules for calculating runtime. The what if there's an if else, what if there's a loop, what if there is a nested loop, what if there is a recurrence relation, and what if there are consecutive statements. And then you need to know what asymptotic notations are, their basic definitions, and what they mean mathematically, how functions grow with respect to each other. So you can plot by trying different values of n in increasing order and see how the functions behave and how their plots will look like. You can even write some simple program to plot graphs for a function and then see how they grow as n increases. And then you have to know how to solve recurrence relations. What are the different methods? And this is the last method you need to know, which is Master's theorem. So the mathematics part we have done. So when we go ahead and study different types of algorithms, we will refer to these O notations, or we refer, for example, when we get a recurrence for a particular algorithm, we'll say this is, let's apply Master's theorem and see what the runtime is. And we can also evaluate the runtime after looking at the algorithm itself by seeing how many loops are there and how. So we are going to apply all of this. What follows is different studying different types of algorithms with specific examples, not writing exactly the code for that, writing a pseudo code for those algorithms, then evaluating the pseudo codes to see what the runtime of the algorithms is going to be. Many times you'll have reconciliations, and then we'll get back to this maths on how to find the runtime from the reconciliations. Okay, so I'll put up this and I'll try to give you your first assignment also. From next week, we will start with the first algorithm type, which is divide and conquer. Okay, because we have already done merge sort, quick sort. We'll go over the pseudocode part quickly, and then we'll just go at the analysis and a couple more examples in divide and conquer. Okay, so I think we'll stop here today. Aman, please take a screenshot of for the attendance.
Yes, ma'am, I have taken screenshots.
Okay, so don't take screenshot in the beginning and then people will come and leave.
Ma'am, actually, I take in between, in between the class at a time interval which is midway.
Okay, fine, that's okay. Uh, all right, any questions? No questions? So that means everything is very, very clear. Yes, okay. Okay, in case you want to, if you have any questions, I don't know, you have a raise hand option here or not? You can raise your hand in case you want to ask anything. Okay, fine. Then we'll end the class here. I'll post these notes later on, and maybe I'll give you one assignment by Sunday regarding these topics, lecture 1 to 4. All right, thank you.
Thank you, ma'am.
Thank you, ma'am.
Bye.
Thank you, ma'am.